Okay, so here's a question nobody ever asked you. And once you hear it, you're going to be annoyed that nobody asked it sooner. Why did you trust them? Not in a dramatic, conspiracy theory, lizard people way. In the totally boring, completely mundane way where you were 7 years old and an adult with a laminated badge handed you something and told you it was fine, and you just believed them. Because what else were you going to do? You were 7. You had a juice box and a lot of feelings about recess. You weren't exactly running independent risk assessments. But here's the thing. Some of that stuff, not fine. Not in a you're going to die tomorrow way. In a, it turns out the official story was a little light on detail way. The kind of thing where you do 5 minutes of actual research as an adult and you get this very specific feeling, like you're reading the footnotes on your own childhood and the footnotes are raising some questions. This is about that feeling. Not all of it is scary. Some of it is just weird. Some of it is genuinely, okay, who signed off on this and why did they still have a job afterward? But all of it is stuff you probably still half believe because nobody ever circled back and said, hey, actually, about that thing we said. So, let's go. Start with the one that still lives rent-free in most people's heads. Lightning can't strike the same place twice. You heard this as a kid. You believed it. You have probably repeated it as a fact to at least one person in your adult life. Maybe in a thunderstorm. Maybe while standing somewhere high up feeling smug about your knowledge of atmospheric electricity. It's not true. It's not even a little true. It's the opposite of true. Lightning actively prefers to strike the same places repeatedly because lightning isn't random. It's lazy, in the most technical sense of the word. It's looking for the path of least resistance. Tall things, pointy things, conductive things. The Empire State Building gets struck by lightning about 20 to 25 times per year. The same building, every year. So many times that they actually have equipment to monitor it because it's that predictable and that frequent. The saying comes from a misunderstanding of probability. People think, lightning struck here, so the conditions that make this spot a target must be gone now. But that's not how it works. If lightning struck you once, it struck you because something about you made you a target. And that thing is probably still true. You are still tall, still metal, still standing in a field. The lesson schools should have taught. Probability doesn't have memory. The coin doesn't know it landed heads 5 times in a row. The storm doesn't know where it's already been. And if you're the tallest thing in a field in a thunderstorm, the fact that it already got you once is not a protective shield. It is, in a dark way, evidence that you are exactly the kind of target it's looking for. Now, why did this become a thing people say? Probably because it sounds like wisdom. It has the rhythm of wisdom. Philosophers used to use it as a metaphor for hardship. If something terrible already happened to you, surely fate won't pile on. Comfort disguised as meteorology. Except lightning doesn't know you've been through a lot lately. Lightning has no idea about your situation. Let's talk about something you touched about 800 times before you were 12. Pencils. The old assumption, still drifting around in the cultural atmosphere like a low-grade fog, is that pencils contain lead. That you could theoretically poison yourself by chewing on one, or jamming one into your hand on a dare, or doing whatever bizarre thing children do with pencils when they're bored in class. Here's the thing. Pencils have not contained lead since approximately the 1500s. The gray stuff in the middle of your pencil is graphite, a form of carbon, not a heavy metal, not a neurotoxin, not something your body is quietly filing away in your organs for a revenge it's planning later. Graphite, named for the Greek word for writing, found in metamorphic rocks. Completely different element, completely different molecular structure, completely different toxicity profile, which is to say, basically none. The confusion happened because when graphite was first discovered in England in the 16th century, people thought it was a form of lead. They called it plumbago, from the Latin for lead. The name stuck for a while. The actual lead did not. Manufacturers figured out pretty quickly that graphite wrote better, was more abundant, and, this part I imagine helped, didn't slowly poison the people making the pencils. So when your teacher told you not to put the pencil in your mouth because it was made of lead, they were passing down a linguistic ghost. A word that survived long after the thing it described had been replaced. Nobody updated the folk warning. Nobody sent a memo. The pencil moved on. The warning didn't. This one matters slightly less for your survival and slightly more for what it tells you about how information travels. A scary-sounding thing gets said once, by someone who heard it from someone else, and it just circulates indefinitely, even after it stopped being true. Even after it was never really true in the way people understood it. The vibe of the warning outlives the accuracy of the warning by about 400 years. The one about blood is where things get genuinely weird. At some point in school, maybe biology, maybe health class, maybe some laminated poster on a classroom wall, you were told that blood is blue inside your body and only turns red when it hits oxygen. Some of you believe this hard enough that you still feel a tiny flash of, wait, but when someone challenges it. That's okay. That flash is what we're here for. Your blood is not blue. It has never been blue. Inside your veins, outside your veins, in a vacuum, in a jar, on a shelf, red. Always red. The hemoglobin in your red blood cells contains iron, and iron compounds are red. Deoxygenated blood is a darker, more muted red, less bright, more maroon, but it is not blue. It has never been blue. The reason veins look bluish through your skin is not because the blood inside them is blue. It's because of how light penetrates and reflects off skin tissue. Different wavelengths of light get absorbed at different depths. Red light penetrates deeper into tissue and gets absorbed. Blue and violet light bounce back from shallower layers. So your brain is processing the visual input through your skin as bluish because that's what the physics of light through skin produces, not because the thing underneath is actually that color. Your blood is red. What you're seeing through your skin is a perception artifact, not the blood's actual color. You are, in a very small way, mildly hallucinating the color of your own veins. The blue blood myth is interesting because it fills a gap that feels real. Veins do look blue. Blood in the body does behave differently than blood outside it. There's a version of the real explanation, oxygenated versus deoxygenated hemoglobin, that sounds kind of like what people say, except for the crucial detail that deoxygenated doesn't mean blue, it means darker red. Someone, at some point, collapsed that nuance down into a more dramatic story. Blue versus red. Inside versus outside. It's a clean narrative. It's just wrong. And once it's in a poster on a wall, it lives there. You absorb it like background radiation. You're 30 now, and you still feel faintly uncertain about this, even though you just read the actual explanation. That's how sticky wrong information is when it gets in early. Here's one that requires you to think back to something that definitely happened to you. Someone at school told you, maybe a teacher, maybe a fire safety presentation, maybe both, that if you're on fire, the thing to do is stop, drop, and roll. You almost certainly practiced this. There may have been a carpet involved. You dropped to the ground and rolled around while a teacher watched. And you learned that this is what you do if you are on fire. Stop, drop, and roll is real. It works. That part is fine. What's less fine is that schools almost universally skip the part about when it applies, which is specifically and only when your clothing is on fire. And they skip the thing that actually kills people in most fires, which is the smoke. According to the National Fire Protection Association, smoke inhalation causes the majority of fire-related deaths, more than the burns themselves. The fire safety training most kids receive in school focuses heavily on what to do if you're literally burning, which is dramatic and memorable and makes for a good floor rolling exercise. It focuses much less on stay low where there's more oxygen. Feel a door before you open it. Know your exit before you need it. Don't assume the hallway is clear. Don't go back for things. The stop, drop, and roll training is real fire safety. It's just the small, dramatic, physical part of fire safety. The part that looks good as a demonstration. The part that kids can practice in a gym. The less photogenic part. The part about smoke. About air quality. About how disorientation happens fast and confidence about your exit route can get you killed. That part is harder to make into a floor exercise. So it often just didn't make it into the lesson. Not malicious, just a bias toward what's teachable in a 30-minute assembly. But the effect is that an entire generation of people have a very clear embodied memory of rolling around on the floor and a much fuzzier sense of what to actually do in a real building fire. Let's do one about nutrition, because school nutrition messaging was its own genre of well-intentioned confusion. The food pyramid. If you went to school in the 90s or early 2000s, you got the pyramid. You got the poster. Maybe you colored in a worksheet. The pyramid said, lots of bread at the bottom, then vegetables and fruits, then dairy and protein in smaller portions, then fats and sweets at the top. The tiny triangle of shame, to be eaten sparingly. Here's what the pyramid didn't tell you. It was heavily shaped by agricultural lobbying. The USDA, which created the pyramid, also represents American agricultural interests, meaning the government agency in charge of telling you what to eat is the same one responsible for supporting the industries that produce the food. That is a structural conflict of interest so baked into the system that most people inside it probably didn't even clock it as a conflict. Researchers at Harvard, including Walter Willett, who was for a long time the chair of Harvard's Department of Nutrition, were publicly critical of the original pyramid. Their critique? It lumped all fats together as bad when the science was already clear that different fats behave differently in the body. It lumped all carbohydrates together as fine when the science was already clear that refined carbohydrates and whole grains have wildly different metabolic effects. It placed dairy as a near-essential food group in a way that was not fully supported by the science and was very fully supported by the dairy industry. The pyramid was not a lie. It was not a conspiracy. It was a document that tried to represent nutritional science while simultaneously being acceptable to every agricultural industry that would have lobbied against it if it said, "Eat less of our product." The result was a compromise document dressed up as a nutritional authority. You got it in school. You thought it was just what scientists had figured out. It was science mixed with politics, mixed with economics, filtered through a very simple graphic that a child could color in. The pyramid got replaced in 2011 with MyPlate, which is better in some ways and still subject to the same structural pressures. The lesson isn't that you shouldn't eat bread. The lesson is that nutritional guidance that comes from a government agency, whose job also includes supporting agriculture, should be read with at least one eyebrow slightly raised. Not dismissed, but not received as pure, neutral science either. The one about gum is quick and worth including just because it's so specific. If you swallowed gum as a kid, there is a reasonable chance an adult told you it would stay in your stomach for 7 years. It won't. Your digestive system can't break down the gum base. That part is true. The gum base, which is the chewy synthetic polymer component, is not digestible. But not digestible doesn't mean sits there forever like a debt you can't pay off. Your digestive system is very good at moving things through that it can't break down. The gum base exits the same way everything else does. It just doesn't get absorbed. It's fiber's annoying cousin. The 7-year claim has no scientific basis. It seems to have originated as a parental deterrent, a thing adults said to children to make them stop doing something gross and mildly inconsiderate, which is understandable. It's much easier than explaining the actual mechanics of gastrointestinal transit to a 9-year-old. But then it just became a thing people believed, into adulthood, into confidently repeating it to other people who also believed it. The only real concern with swallowing gum is if you do it in large quantities over a very short period, in which case it can, in rare cases, cause a blockage, specifically in young children whose digestive tracts are smaller. There are a handful of documented medical cases. It is real, but it is extremely not common, and it is not 7 years. The reason this one's worth pausing on? The deterrent worked so well that it survived a thing it was meant to deter. Children eventually stopped swallowing gum in most cases. The myth didn't. It just got decoupled from the behavior and floated away as a freestanding fact. People who haven't swallowed gum in 25 years still believe this. Okay, last one. And this is the one that actually has ongoing implications for your adult life. Sunscreen. Not that sunscreen is bad. Sunscreen is good. Use it. That's not the issue. The issue is that most people were taught that sunscreen means you're protected from the sun. Full stop. Apply it, you're fine, go outside. And the SPF number, most people understand it as a dial that goes from a little protected to very protected in a linear way. SPF 15 is okay. SPF 50 is better. SPF 100 must be incredible. Here's what the number actually means. SPF 15 blocks about 93% of UVB rays. SPF 30 blocks about 97%. SPF 50 blocks about 98%. SPF 100 blocks about 99%. That seems like a small difference until you remember that the difference between 93% and 99% is not nothing. If a million UV rays are hitting your skin, SPF 15 lets through 70,000 of them. SPF 100 lets through 10,000. Still a meaningful gap. But here's the part that's more important than which SPF you buy. None of those numbers stay true for longer than about 2 hours, and they certainly don't stay true after you sweat or swim or towel off. Sunscreen degrades. The protective compounds break down through exposure to the exact thing they're protecting you from. Most people apply sunscreen once and consider themselves protected for the day. This is not how sunscreen works. This is how people get sun damage while feeling like responsible adults who definitely put on sunscreen before they left the house. SPF 50 applied once at 10 in the morning and never reapplied is less effective than SPF 30 applied every 2 hours. The reapplication is the mechanism. It's not a suggestion. Schools taught sun safety. They did. But the messaging was usually, apply sunscreen, not apply it, reapply it every 2 hours, know that no SPF blocks 100% of UV, know that UVA rays, the aging and deep tissue damage kind, require broad-spectrum coverage specifically, and know that being in the shade or under clouds doesn't mean you're not getting UV exposure, because up to 80% of UV rays pass through cloud cover. You are almost certainly getting more sun damage than you think you are, because you were taught the headline version of sun protection and not the actual operating instructions. Here's what connects all of this. It's not that schools lied. It's not that there's a curriculum committee somewhere cackling about pencil lead and blood color while the populace stumbles around misinformed. It's something more boring and more interesting than that. The version of things that gets taught is almost always a simplified version, which is necessary. You're teaching children, and children don't need the full literature review. But simplified versions have a failure mode. Sometimes the simplification removes the part that actually mattered. The blue blood thing? The real explanation involves light physics and hemoglobin saturation, and that's a harder lesson, and blue on the inside, red on the outside is a cleaner story. The food pyramid? The real story involves lobbying and agricultural economics, and the difference between saturated fats and unsaturated fats, and that's a messy lesson, and a pyramid with big, colorful sections is a cleaner picture. And then the simplified version just runs, uncorrected, because nobody comes back to you in your 20s and says, okay, so remember that thing from 4th grade? We need to revisit some of that. You're left with the childhood version of a story about the world, and you carry it into adulthood unless something specific dislodges it. Which means the actual skill, the one that would have been more useful than any individual fact, is knowing that every explanation you received has a level below it. But what's actually going on there, that you can always go one layer deeper on. Not because everything you learned is wrong. Most of it is fine, but because the simplified version is never the whole version, and sometimes the part that got left out is the part that changes what you'd actually do. The lightning thing, the sunscreen thing, the fire safety thing. In each case, the missing information isn't trivia, it's operational. It changes the decision you'd make if you had it. You were handed a cartoon map of the world when you were small, which was appropriate and kind and necessary. But the map got a little sticky, and some people still navigate by it. The ones who don't are not smarter. They just stayed curious after the lesson ended. They kept asking the version of the question that starts with, okay, but actually though, that's the whole move. That's always been the whole move. Ask one more time.